Okay, so let's get started. Yeah, so this is one course where we have to start by kind of defining what the course is all about, what the phrase artificial intelligence means for our purposes. Okay, so the first slide kind of creates a working definition. Uh, we know they exist in the world. They are biological entities that live and act appropriately. So that word appropriately, notice, is highlighted in the world. So appropriately, right now we will kind of leave undefined. But one way to think of it is that any entities that live in the world will try to survive in that world and try to live as long as possible, right? So whatever changes they make in that world are going to be appropriate. You can define other ways. This is a very simplistic definition of appropriate, but uh, you have an intuitive idea of what this appropriate means. Okay. Now, intelligence, again, we are going to just define it as the abstract ability or capacity that allows humans to live and act appropriately. So, uh, so we are leaving some things undefined here. In particular, we are leaving appropriately sort of undefined. We are assuming we have an intuitive idea of what it is. And finally, artificial means it's human made. Okay. So our working definition for AI is going to be the following. AI is the science and engineering of building sustainable communities of artificial agents. So artificial agents means that we are going to construct these agents. Agents are entities which basically live and act in the world, right? So there will be communities. So it's not necessarily always just one agent that you build. Well, most of our stuff will be, of course, concerned with just a single agent, but it doesn't restrict us to that. So it will be the science and engineering of building sustainable communities of artificial agents that cohabit and act appropriately in a world that contains other entities, right? That contains other agents. Now, these agents may be humans, or these agents can be other artificial agents. So this is the kind of broadest definition of AI that we will start with. This is our working definition. And in short, then, what we want to discuss in this course is how to build these artificially intelligent or artificial intelligent agents, right? So that's our working definition. Now, how do we, so once you have such agents in the environment or in the world, how do you, test for whether an agent is an artificial agent, artificially intelligent agent, or is not one? And for this, there is this game which Alan Turing, a well-known computer scientist who also gave us the Turing machine, defined, right? He called it an imitation game. So it's a game between a known human agent and an unknown agent. And the goal of the game, or the aim of the game, is for the human agent to be able to interact with this artificial, or we don't know whether it's artificial or not, the second agent, just let's call it the second agent, and determine via interactions whether this second agent is human or artificial. Okay, that is the goal. So in the original paper or the original game that Turing devised, this is a 1950s paper, and it's something that has persisted to this day, and I'll tell you briefly how. So in the original game that Turing designed, the human interacts with the artificial agent or the second agent only via text, right? So in those days you didn't even have terminals, so you basically interacted with just the teletypewriter or teletext. So the idea is that the human interacts with this second agent via text, and this interaction can be anything. I mean, it's a kind of conversation, if you will. So you can ask the agent about personal things, you can ask the agent about facts of the world, you can ask the agent about what the agent knows or doesn't know. And the goal is, after a certain amount of interaction, whether the human can reliably say the second agent is either artificial or a human, right? So Turing gave some kind of an operational definition of intelligence. If the any agent behaves in a way where you cannot distinguish that agent from a human agent, then we will have to agree that that agent is intelligent, right? So that's an operational definition of intelligence. In newer versions of this test, which is called the Turing test, you allow speech, right? Because now we have fairly decent speech recognition and speech synthesis. So you can actually talk to the agent. And in the so-called further enhanced versions, which is called the total Turing test, you have perambulating agents, which means you have agents with whom you can interact in the real world as if they are moving around. So there are other agents moving around. They can perhaps even look similar to humans. So the looks and those things are not something that you can base your final judgment on. But what you'll have to do is to interact with the agent. So notice that you have to, make your judgment based on the interaction, not upon superficial features. Okay. So this test was actually proposed by Turing in a paper called Computing Machinery and Intelligence. And the interesting thing is that there is a contest called the Loebner Prize, or the Loebner Contest, which has been going on for many years. And every year they have a contest where programs which have been designed, AI programs, can participate in this test. So it's a Turing test. And if the program is able to sort of win the test, then the Loebner Prize goes to that program. So you can go to the Loebner site, loebner.net, and look at how the whole thing works and what program. I mean, what has happened in past years. So this is something that is used, you can say, as a test for intelligence, at least for artificial intelligence. Yeah, please feel free to interrupt me either via, just switch on your mic and ask a question if you need to, or alternately, you can type in your question in the chat box. So don't feel constrained to ask questions or interrupt me simply because we are interacting online. Okay, feel free to interrupt. Okay, so we'll now try to break down this working definition that we had and try to work out the details a little more. Okay, so look at this picture that is there on your screen. So this is a schematic of an artificial agent. All right. So this schematic, you can see, has something in the middle, which I'm calling the AI program, which I've called a soft brain. Okay. So this AI program interacts with the environment, and basically what this AI program is doing is going repeatedly or rather executing repeatedly what is called a sense act cycle. Okay. So the outside world has sensory data that impinges on the sensory modalities of the soft brain or the AI program. So just imagine that you are this agent, right? Or you are this thing. So you have eyes, so you are able to see, you have ears, so you have auditory input, you have visual input, you may have tactile input, you may have input regarding smell, you have linguistic input, and so on. So imagine that you have these sensory modalities and that you have the environment which can give you these inputs. So it can give you visual input, auditory, tactile, uh, smell inputs, and so on, all the sensory inputs. So let us assume that so that's the outer layer. Okay, so that's the sensing layer. So these could be in a artificial agent of sorts. For example, these could be cameras, these could be microphones, these could be tactile devices, and so on and so forth. Right. So imagine a robot which has all these devices. So you sense the world or the environment, and this sensing has to be finally represented. So you have these perceptual representations. So there are these three layers of representations. The first one, where the sensory information is directly converted into some kind of internal representation, which we are calling percepts, or equivalently perceptual representations. Then these can be abstracted out into so-called conceptual representations. And finally, you could have representations which are meta representations, which are representations of multiple concepts linked together and so on, which we are calling tertiary representations. So now, whether the humans work that way or not, we cannot directly say at this point. But there's good evidence that we indeed do use representations, right? And approximately something like this is true even for humans. So you have, there may be more layers in the human system. So the percept itself may consist of multiple layers, right? But something of this kind, there is reasonable evidence that something of this kind happens in the human system as well. So this is a good working model to start with. Okay, so you have so these representations are very important when you build an artificial agent, because if you do not choose the right kind of representation, then it's possible that you may have, or you may not be able to work with it properly. So just imagine if you had to do mathematics with Roman numeral representations, right? So the place notation based in representation that we are all familiar with, that's how we represent numbers. And all the operations that we do on those numbers, they are representations, remember, of some abstraction called number. Let's for the moment think of just positive integers. So all addition, multiplication, division, all the operations that you do are efficient, simply, and can be done effectively and simply. Just imagine doing the same thing with the Roman representation of numbers. So the choice of representation can be critical when you actually manipulate representations. And clearly that is what this soft brain or an AI program will do, right? It's going to manipulate representations to come up with other representations which may be useful. All right, so now we'll go into slightly more detail. So notice that there's an environment and there's this AI program, which is the soft brain. So to be able to build these such programs, we need to go into a little more detail about also the kind of environments that AI programs may encounter, and also the types of agents that we may have to build, right? From very simple agents to fairly complex agents. So what you want to do now is to kind of classify these things a little bit. Okay? So, so now we are going to look at what are the attributes. So this whole thing is called the task environment. Okay, this environment, this is the task environment. So this is where the agent is going to act. So you can think of it as the world. This is where the agent is, and this is the where the agent is going to act. Okay, so we call this the task environment. Now this task environment has attributes. Okay, so what are these attributes? So we can kind of define various attributes here. So the task environment may be fully observable or maybe partially observable. So partially observable may mean also you can't see anything about the environment, that is not observable, right? Fully observable means that everything that is there in the environment can be sensed by you. Okay, partially observable obviously means that everything that is there in the environment is not available to be sensed by you. By when I say you, I mean the AI program or the AI agent. Okay, so it's once again the reference is always to this picture, right? The AI program, so notice that it is going to sense the environment, right? Here it's going to sense the environment, then process the percept or whatever based on whatever it has received as the sensory information. There could be histories, there could be knowledge and other things inside here in the program, and then it decides to act in the environment. So it may change the environment or it could do something else. Okay. Yeah, so we'll see examples of this. So somebody has said what could be examples. We will see different examples. Yeah, I'll give you examples of everything. Don't worry. Okay, so let's look at something like a say simple. Let's look at games. Okay, so if you look at the look at a game like chess, for instance. So what is the environment here? So you have actually two agents here. You have two players, but both players can see the full board, right? They can see the clock or whatever. If you're using a tournament system, then the clock is there and so on. So everything about the environment, you can't see inside the second agent. Neither agent can see the second agent's insides, which means what is going on in the mind or of that agent. Okay, so that's okay. That is not something that anybody can sense. But so far as the board is concerned, you can say that it is completely the current state of the board tells you everything about the game, right? And that is fully observable. On the other hand, let's take a game which is, let's say, a game where it's a card game, okay, poker or something of that kind. So clearly, in those cases, you are able to see your own cards, but there are other cards which are important for the game, but you are not able to observe it. Okay, they are not visible to you. They are part of the game. They play a part in the outcome of the game, but they are not observable by the agent, whichever agent. So if there are multiple players, my cards are visible to me but to nobody else, and similarly somebody else's cards are visible to that individual or that agent but not to the others. To take another example, let's look at for example, a household. Okay, imagine a robot which does household work. So once again, household work may involve many things, right? It may involve cooking, it may involve cleaning, it may involve other things, moving things from one place to another, and so on and so forth. So assuming that the household work, for example, involves cleaning right now, cleaning the house, for example, if the agent is cleaning something in a particular room, the agent is able to see things in that room, but is not able to, of course, see things in another room, or there's no way the person can sense other things in the house. So if this is a, say, cleaning agent, just a cleaning agent, a household cleaning agent, forget about the other things. So that is, forget about cooking or forget about moving things around and so on. It's just, let's say, cleaning. So the household agent's environment is the whole house. but what you are able to see is only part of the house. Okay, even if you are in a room, it's possible that you are only able to see something that is in, you know, that is not occluded. So you may be able to see only part of the room. So while you are, clearly you have to sense dirt wherever it is and clean it. So it is quite possible that you are not able to sense dirt in areas which you are unable to see, right? Let's say the robot has cameras or whatever and is able to see, so you are not able to see. So once again, this would be a partially observable environment, right? So mostly you will see as we go along that mostly the real world, or if you want to build such a cleaning agent, you have to assume that this agent is not going to be able to see everything. So what is the implication? So when an environment is partially observable, the implication is that you have to build in the ability for the agent to sample the environment, or different locations in the environment, or the more generally the environment as a whole, repeatedly, right? So for example, if the agent has only cameras in the front, that is like we have eyes and can't see 360 degrees, then if the agent is cleaning something, can't see behind. So if something falls on that side and dirties the floor or dirties something, the agent has no way to observe it, right? So what does the agent have to do? The agent has to sample the full environment that the agent that is part of your task domain, and uh, act accordingly. So if for example, if it's a house and that has multiple rooms and the agent is cleaning a house, and even if the agent has 360-degree vision, it cannot know what is going on inside another room, right? A different room. So so that would mean that you have to go to the other room, sample it, see if everything is clean, go to the next room, and so on. So keep sampling the house to make sure that whatever your task is to keep the house clean. You complete your task, or you do your task satisfactorily. So that is something that one has to bother about. So if it is fully observable, like if it is chess, the board can be represented fully observable. Both agents, both player 1 and player 2, can fully observe it. So they don't have to keep sampling. The full state is already available to the agent, and the moment there's a change, again that is observable. So you have the full state of the environment or the task domain with you at all times. If the environment is partially observable, that is not the case. You have to write, or your agent has to have a sampling strategy and a sampling method to sample the environment to make sure that the task domain, uh, changes in the task domain are registered, and then you have to act suitably. Okay, the next attribute is this one, which is basically the attribute of whether something is deterministic or non-deterministic, right? Now this can be defined a little more precisely. So let us say S and S1 are states of the environment, right? And A is an action. So remember, we basically sense the environment, then we process whatever we have sensed in the context of whatever knowledge we have about the past or about anything. And then based on that, we come up with an action which includes no action. You may not want to do anything, but uh, in general, you will come up with an action A. Okay, so you have a set of states, you have a set of actions, and S and S1 are two states, and A is an action. And typically, when the state S, comma A leads to a new state S1, and S1 is completely determined by S and A. So S and S1 are states of the environment. So if completely determined by S and A, then you will say that it is deterministic, except for other agents, right? So other agents are autonomous and can do whatever they want. But so far as the agent in question is concerned, if that for that agent you have completely determined outcomes, that is S1 is completely determined by the state S and the action A. So for example, in the chess situation, if the agent makes a move, okay, senses, I mean the board is in front, so it's fully observable, and it decides to make a move. It makes the move. The resulting environment, in this case the resulting state of the chessboard, is completely determined, right? So it's completely determined, and therefore it's a deterministic environment, task environment. Okay, you can't, of course, know what the other agent or your competitor or the person across the board is going to do, but when you do something, you are completely sure what the change in the environment is. Okay, so if this is not possible, then it will be called a non-deterministic environment. And if you have a situation where uh, the non-determinism is probabilistic, that is, it's stochastic, which means you can define it via a probability distribution, then you call it stochastic, right? The more general term is if it's not deterministic, is non-deterministic. But if the final situation is uh, probabilistic, then you can define it, you call it stochastic. So that is, it can be modeled via a probability distribution. So, so probabilistic ones, most things are probabilistic in the world, right? You cannot fully determine what will happen. So, especially if things are partially observable, you your your action is not going to completely determine the state of the environment, right? There may be other things happening in the environment, irrespective of the other agents, not including other agents. Other things may be happening which change the environment, and so you cannot say that, for example, even if you take that simple cleaning example that we looked at a little while ago, uh, because I'm cleaning here, I know the state as of now for the current room. I don't know what's happening in other rooms. Okay, somebody may have dropped something there, or because of some other reason something may have gotten dirty, some dust storm has come and dust has come in through some window in some other room, whatever. There could be, infinitely many ways in which something gets dirty in the other room without this agent knowing, because it's partially observable, and therefore the action that I do, the cleaning action that I do in the current room, does not determine the state of the environment, in this case the whole house, and therefore it's non-deterministic, right? So if you look at the real world, that is the case most of the time, right? Deterministic is much more uncommon. Then you have the property of whether something is episodic or non-episodic, right? Non-episodic is often called sequential, but basically what it means is that the episode, you have a sense act cycle, and the sense act cycle is complete in itself, right? It does not lead. So if I do something right now, I have a sense act cycle right now, that does not affect future sense act cycles, right? So once again, it is a rare situation in the real world where this is episodic, right? There could be some few cases which are episodic, but in many task domains, remember it's in the task domain, one is not really looking at it in totally open sense. So if you are, for example, cleaning, or let's take the game. So in the case of a game, yeah, is there a question? What is sense act action? Sense act action is what I showed you here, right? So you are this agent. Just imagine now, instead of this, it's a human being. So what happens if you are a human being? Let me. It's this. It's not creating a fresh page, but anyway, let's just live with this for the moment. So imagine I was here. So imagine I have this as a human. Then what happens if you are doing something? Let's say you are cleaning. What do? You look around, you see whether there's some dirt somewhere, and then you see that dirt, you observe it and decide it is dirt, and then you go and clean it. So you sense and then you act. And pretty much all behavior in the world is a sense act cycle, right? Even as I'm sort of lecturing right now, I am looking at the slide. I want to convey what is on the slide, and I use the slide, I sense that slide, and then I use some knowledge which is there in my head, and I act, which is I speak out something, right? So pretty much all behavior can be modeled as a sequence of sense act cycles. Now, take for example the fact that I am lecturing right now, right? So, if you look at this sense act cycle, so if you look at that sense act cycle, what do you see? I mean, is it episodic or is it sequential? Right? Clearly, it is sequential, because what I am saying now is obviously dependent on what I said a little while ago. So I cannot, nobody would normally speak totally disjointed random sentences where there's no connection between what was said earlier and what is being said now. So there is this sequentiality, or there is a dependence on the past, right? So most actions or most task environments will have the sequentiality property. Okay. Very rarely will you come across environments where something is episodic. That is, you have a sense act cycle, and that does not have any impact on what you do next. So, for example, one could imagine that if you are a cleaning agent, you see some dirt, you clean it. That is one episode of cleaning, and it does not really have any impact on what you will do next, right? So what you will do next will, of course, be look for dirt again, and when you spot dirt, you will go and clean it again, right? When I say look for dirt again, in that itself may be complex, in the sense that if it's a multi-room house, you will go from one room to another, so navigation is involved and so on. So, and then you will look for dirt in that room and then clean it, right? But if you look at the act of sensing dirt and cleaning, that is episodic. Once you have done that, it is one episode of cleaning or one sense act cleaning cycle. It does not change anything, right? Change anything in the sense, it of course removes the dirt, but your next action will again be pretty much start from scratch. Look for dirt in the current room. If you don't have that, if you don't have any dirt, then sample other rooms. Is episodic environment not? See, these are independent, right? It could be non-determinism is essentially whenever you have observability, non-determinism will be kind of pretty much automatic. You're talking about the state, right? The state of the environment cannot, if it's partially observable, like in this particular thing, if you look at house cleaning, then it is really a sequence of episodes where each episode does not affect the next episode. So if I'm cleaning a certain place, certain area, I clean it, that's over. Where I clean next is completely independent in some sense. I look for dirt again, and that looking for dirt in itself is a sense act cycle, which means I look for dirt. If I see dirt, I clean it. If I don't see dirt, I will navigate to some other place. So I will have some way of navigating so that I cover the whole house. Okay. So this is an episodic way of doing things, but it is non-deterministic. What is this? Would the fact that the room just clean would not need to be checked, not make it sequential? No, it does not. Actually, it does not, right? When you are cleaning dirt, this you will basically you have cleaned something. You check whether it's clean or not. If it is clean, you move on to cleaning something else, right? So it is episodic in that sense. That is, search for dirt, clean, search for dirt, clean, search for dirt, clean. That cycle keeps happening, and that cycle uh, is episodic because you are my search for dirt clean in one cycle does not really affect the search for dirt clean in the other cycle. I mean, you can take an extreme case where I search for dirt, clean, and even as I'm cleaning the area where I had searched for dirt and found dirt, maybe something else falls on it, right? So once again, if I go into the cycle, I may end up cleaning the same area again. But overall, it is episodic. It doesn't really, because it's partially observable. It doesn't. It's non-deterministic, but it does not really, there's no sequentiality in it because my cleaning episode is not going to affect anything else. My next cleaning episode is not going to directly be affected by this. That's not true, for example, in lots of other cases. For example, if you're looking at a self-driving car, for instance, okay, or a self-driving taxi or something like that, then clearly what you are doing is going to matter. So if you are accelerating and you suddenly see you have reached a red light, then you will or you see somebody is crossing at a distance, you will slow down, and so on. So the sequence of actions that you do is going to depend on the environment, and it affects what you have done. So if it is you brake, let us say, and you find that maybe there is ice on the road or it's raining and it is slippery, so then your successive braking actions will change. Okay, you may pump your brakes or you may press on them harder or whatever it is. So most environments are not episodic, but there can be episodic environments as well. They are not unknown. Then you have dynamic environments versus static environments. So these are again environments. Dynamic ones are where during the sense act cycle itself there can be a change, right? So again, many environments are dynamic, but some environments will be static. For example, uh, so you call an environment semi-dynamic if the environment does not change with time, but the agent's performance does. Okay. So for example, if you're playing chess, then you sense the environment, which obviously means the current state of the board. And now you're thinking about what is the next move to make. So until you make the move, nothing changes. So, during the sense act cycle, nothing changes. So the chess environment is a static environment. Okay, but it can be called semi-dynamic if the environment does not change with time, but agent's performance does. So that so chess you may call a semi-dynamic environment because as time progresses, I may feel more tired or something like that, right? So my performance may change. But mostly dynamic environments are ones where in a single sense act cycle, the possibility of the environment changing is present. So again, if you have partially observable environments, they will tend to be dynamic. I mean, they do not necessarily have to be dynamic. It depends again on the task domain, remember. But if it's partially observable, the chances are high it will also be dynamic. Then you have the notion of discrete versus continuous. Okay, so discrete versus continuous is how time is sort of modeled in the task domain, right? So, for example, if you look at this chess game we were talking about as an example, you could model it as a discrete case, right? So you can imagine that, as a matter of fact, there is a clock, right? In a tournament game, there is a clock. So I look at the board and I know the state and I'm thinking, I make the move and I hit the clock. So every time I hit the clock, basically that is the time at which, they're discrete times. So time is flowing, of course, but I hit the clock to say that, okay, now this is the point at which you will need to again look at the board to see the changed state because I made the move. And the opponent does the same thing. So in between, nothing is important or nothing happens. Okay. So it's a discrete nature of time. On the other hand, of course, lots of other things are continuous, right? A self-driving vehicle would have to model. I mean, it's the environment is continuous, right? So you'll have to decide. I mean, the whole sense act cycle is happening in real time. Then you have single agent versus multiple agents. And within that, that is whether your model you are looking at a task domain where there's only one agent, okay, or whether there are multiple agents. For example, if you're looking at a situation like a chess game, there are multiple agents, and it's a competitive situation. The agent, I mean, each agent is trying to compete with the other, is trying to win, or it could be a cooperative multi-agent task domain. For example, if something very heavy is being carried by, say, one robot cannot hold it, or it's too heavy, so you require multiple robots to hold it and move it from one place to another. This would be a cooperative task domain. So you can have single agent versus multiple agent. And then another dimension of variation, which I think is not here. I'll just write it here. I'll add it later. That's known versus unknown. Okay. Known versus unknown. Will multiple agents have a head agent? No, not necessarily. They could be peer agents, right? So there is no necessity to have a boss. So all agents will see that, like this, for example, how you carry a heavy load, something where multiple people have to cooperate to carry it. So how do you do that? I mean, each agent kind of decides how whether the load is too much or not, and informs the other agent, why don't you take a little more load on your side, and so on and so forth. So you don't necessarily have to have a single controlling agent in that. I mean, that's one possibility, but the other possibility is that all agents are, uh, you know, doing it cooperatively without one of the agents being, a decisive agent. Uh, yeah. Clearly, many of these things will imply other things. So, like partial observability implies many things. It implies that you will have mostly a non-deterministic or stochastic environment. It will also mostly often mean that sequential, dynamic, and so on. Well, dynamic not so much, but yes, if you have multiple agents, the possibility that it will be a dynamic environment is obviously much higher. I'm sure you could think of a situation where you have multiple agents and the environment is not dynamic. For example, uh, chess. You have two agents. I mean, two programs. Let's say playing against each other. They're competing agents in this case, not cooperative. But it's not really dynamic, right? During a sense act cycle, when I am playing, it's my turn to play. Nothing else changes until I play. Nothing changes. And similarly, when the other agent's turn is there, until the other agent plays, nothing changes. So lots of game environments, for example, uh, things would be non-dynamic when you take turns. Multiple agents may be present in the game, but it may be a static environment. Okay. I was talking about known versus unknown. Okay. This thing actually relates to the fact that the environment is something which has its own behavioral sort of uh, laws. Okay, so the real world, the physics of the real world, for instance, doesn't depend on me. There is gravitation, and there are other electrical, magnetic forces, and all that. The world works irrespective of me, the agent. Okay. Uh, Now, how much do I know about the environment? I may have complete knowledge of that environment, or I may have only partial knowledge of that environment, or I may have no knowledge of that environment, right? So now remember, this is a task environment, right? So supposing I have to play, they say the artificial agent. So we'll just keep calling it agent henceforth. I don't want to keep saying artificial agent and so on. Pretty much the same thing applies to humans also. So it's not really that humans are that different. But take a situation where an agent has to play a video game and knows nothing about the video game. Okay, then how will the agent play? The game is up on the screen, and you'll have to, you know, do trial and error, explore and find out, and essentially, work out how the whole game works. Uh, so imagine what happens to humans also. So you are born as a baby, and the outside world has its way of working. The real world works in certain ways. There are the laws of physics and chemistry and all that which actually govern the outside world that you are in. You know nothing about it. Pretty much you know nothing about it. Okay, but you as a baby start learning. You start learning about the environment. Okay, so it's an unknown environment for you, totally unknown when you are just born. But you start learning. Okay, you start learning motor. So slowly you learn to walk. You learn other motor sort of programs. Not just walk. You learn to run. You learn to have more coordination with your hands and feet, and so on and so forth. Of course, you learn language, and you learn about the world, right? So, so you may have a task environment or a domain where, for example, things are unknown. And again, that's not an uncommon situation. Most of the time we work in environments where we don't know everything. But again, there will be environments, task domains, where you know everything. For example, once again, if you look at the game environments, you may know, if you are a chess player, you will know all the rules of the game, right? So that means that it's a known situation. But in the real world, very often we don't know everything. So this is different from, okay, this is different from, the partial observability or the stochasticity of the environment as to that something may happen. It's different from that. Here, basically like chess, I know the rules of the game. I know how each piece moves. I know how all the rules of the game, right? As a player, I know that. So, so it's basically the rules of the world, the environment, or the task domain. What are the rules, or what are the laws of the task domain, and whether you know them or not. If you don't know them, or you know them partially, so you could have a hybrid situation where you know them only partially, then you will have to learn. You'll have to learn them. That's what we do as we grow up, right? Not just grow up, we do that all the time. For example, till you die, you pretty much all the time learning. You don't know everything about the world. So if you kind of look at these dimensions of variation of the task environment, the nature of the representations, the nature of the algorithms which we will use and all that depend a lot on this. So it's useful to characterize the environment in a proper way, right? So this is important. This gives you a handle on, coming up with the science and the engineering, they're coming up with designs which will work suitably in the environment. So it's always useful to ask these questions about your environment, right? And now let's look at some examples. Okay, so if you can read it, I'll continue. Something has gone wrong with my display here. It's not zooming for some reason. Okay, so here you see, it's trying to uh, look at a task environment. So let's say you're solving crosswords. F here means fully observable. P means partially observable, and so on. So D means deterministic, S means non-deterministic, that is stochastic or non-deterministic. E means episodic, S means sequential. Here S means static and dynamic, and uh, what was the? This is one agent or multiple agents. If it's one, it's multiple, and the other was discrete and continuous. Yeah. So D here is discrete and C is continuous. So if you look at crosswords, for example, so this gives you an specific examples. You have a program to solve crosswords, then environment is clearly fully observable. It's very similar to chess. So we can just go down the thing. Tournament chess is another thing, fully observable. Self-driving car, partially observable. You can't see everything. Medical diagnosis, similar, partially observable. Part picking, once again, partially observable. Image analysis, you can see the full image, so fully observable. Plant controller, tutor, and chemical structure, again, all of them are partially observable. Similarly, if you look at crossword, then it's kind of deterministic because there's no stochasticity there or non-determinism. So tournament chess is you can say it is deterministic. STR stands for strategic, which means that it is deterministic modulo the other player. So it is deterministic. Self-driving car, medical diagnosis, part picking, they are all again stochastic. Image analysis is again deterministic. Plant controller, tutor, chemical structure, they are all again, you can see, non-deterministic. Okay. So here, for example, crossword, here whether things are episodic or not is clear. They are non-episodic, most of them, because what you do in a particular move, in this case, many of them are discrete, will determine what you do next, right? In most of these cases. So the ones which are episodic is part picking. So you pick a part and that's the end of the cycle. Then you go and pick the part again. I mean, if it's a assembly line, you'll just keep picking the same part. Similarly, image analysis is also episodic. You are given an image, you have to classify it. The next image that you're given has no relation with the previous image. So again, it is episodic. I mean, you just keep classifying the given image. All the others are sequential. Okay. I think there was a question here. Yeah, so the question is the state of the environment, right? The question is, can you explain for chess how it is deterministic? So remember, we are not talking about how the game will progress. We are not talking about that. We are talking about after one sense. Notice what is deterministic thing, right? So deterministic means that if I am in a particular state and I do a particular action, then is S1, that is the state of the environment, is it completely determined, or can it be something else? So let's compare the two cases. Let's take chess and let's take that household cleaner that we talked about. So if I am making the move, the chessboard, the current chess positions, the pieces and all that, the chessboard is the basic state environment. I make the move. Once I made the move, there is nothing else that, so there is a changed environment. So S comma A leads to a new board position, which is S1. And this is totally determined by the action A I make. So supposing I move upon one step forward, the new board position is completely determined. It can't change. right? There's no non-determinism about it. On the other hand, if you look at the cleaner robot, the cleaner robot is cleaning something at one location. It's quite possible the other location. So here, what is the state of the domain? Is basically all the clean and dirty areas in the house, right? So even as I clean a particular area in a particular location, there could be something else could be becoming dirty. So this during the sense act cycle that I have, it's not deterministic. So the state S1 typically would mean that I have cleaned a particular area. Okay, so in my state, that area is now clean, which was earlier dirty. But some other area which was could have become dirty at the same time, and therefore the state S1 is not simply the fact that the area I cleaned is clean, but really something different. So and I can't determine it. My action was clean this area that has become clean, but the overall state of the environment is not determined by this action alone. So that is what is meant by non-determinism. So because of that, it is non-deterministic. So all of them are, so here for example is deterministic. In all other cases it is, S stands for stochastic, which is non-deterministic. Image analysis again is deterministic, in the sense that once you are given image analysis, here really means image classification. So you give me an image, I have classified it, and that's end of story, right? There is nothing else that changes, because the next image is going to come. If I have to classify that image has no relationship with the previous image, and so it's done. My job is done. It's purely deterministic, right? It's determined by the current state, the action I do. After that, nothing. It's both episodic as well as deterministic. Okay, there's a question which says, but in the cleaning example, isn't the environment or state of the house getting changed when one of the rooms is being cleaned? Isn't the overall environment getting affected? Of course it is getting affected. That is the whole point. So the point is that you are going into a new state, S1, when you take the action A, in this case the action clean. But the question is, does the current state and the action clean completely determine the new state? The point is that if that is, it doesn't completely determine the new state S1, then you cannot say it is deterministic. For example, let's contrast the chess and the cleaning example. So let us say that the house is totally clean right now. Only one piece of dirt is there, which the agent is going to clean. So the sense act cycle is, it observes that that there is this dirty tile. Let's just assume the house has tiles. Okay, so all the tiles in the house, let's say it's a floor cleaning robot. All the tiles in the house are clean right now, and there is a one tile which is dirty. So the agent now observes it's dirty, is going to clean the house, clean that tile. As it is cleaning that tile, somewhere else, maybe in some other room, there is maybe the child in the family drops something on the floor, ink on the floor or whatever, right? So now what happens? Now the action is, I have cleaned this tile. The corresponding state should have been that the whole house is clean. All tiles in the house are clean. However, that is not the real state of the house. The real state of the house is that, okay, this is clean, but then the real state is that, okay, the ink has fallen on some tiles in some other room, or maybe even in the same room at the back, elsewhere. So my action of cleaning cleans this particular tile, but it does not determine fully the new state. Okay, because there are other actions which are possible in the environment, not controlled by this agent. So if a situation, that is if a task domain is partially observable, or if there are multiple agents, then pretty much the whole thing becomes non-deterministic. Okay. So does dynamic imply non-deterministic? So dynamic, so sorry. Uh, See, dynamic is that during the environment can change even during the sense act cycle versus static. Yes. If the environment is, I mean, if it is dynamic, then the chances are that yes, it will be pretty much always non-deterministic. Yes. Dynamic will imply non-deterministic. Yeah. So, so these are the, so when you are going to build an AI program, you have to ask yourself, what is the nature of my task domain? And then the design, the design that you'll come up with will accordingly, be sensitive to the nature of the task domain. Okay, the next, okay, yeah, we were looking at these examples. So we have seen this episodic and so on. You have seen the static and dynamic situation here. So crossword, for example, is static uh, because, I mean, similarly, uh, tournament chess is, you can say it is static. Semi is a in-between thing because you have multiple agents here. Here there's only one agent. So if you I don't know whether I've defined that semi thing here. Yeah, it's called semi-dynamic if environment does not change with time, but agent's performance does. So that is possible in a tournament situation. That's why it's being called semi, but forget about the semi part, it's essentially static. Okay. Otherwise, mostly they're dynamic. Right? So finding a chemical structure, for example, is an example of a static. The structure does not change as you try to find it. Right? A program, an agent that basically tries to, uh, given, let's say, a formula and data about the compound. So there are programs now which, if you give, especially for organic compounds, which can be very complex, proteins, for example, what you want to know is the structure of the compound. So chemical structure is three-dimensional structure of the compound, given the formula of the compound and maybe other data. So you may have some data regarding mass spectrometer and various other things, X-ray spectrometry and various other things. Uh, and you have the formula for the compound, that is, you know how many atoms of X, Y, or whatever, how many carbon atoms, how many nitrogen atoms, how many hydrogen atoms, whatever elements are present in the compound. So the formula for the compound. But now what is its three-dimensional structure, right? For biological compounds, this is a huge question. For example, if you're looking at drugs, a lot of drugs work by uh, blocking certain things, and the blocking happens because of structural properties, the three-dimensional structural properties. So that is something then that becomes critical when you're doing drug design. So chemical structure, for example, is again a static uh, problem. Okay, or the environment is static. Then discrete and continuous. So many of these game situations are discrete because they are move based. So that is true. Many real world situations will be continuous, like self-driving car, medical diagnosis, part picking, and so on. Similarly, plant controller. Uh, Chemical structure is also discrete. Tutoring is discrete. So you're really talking about a computer tutor here, that is a tutor agent. Finally, whether something is single or multiple. Okay, so there are some of them which are multiple agents and some of them are single agents. Okay, medical diagnosis, you have the diagnostic agent. The patient is not considered an agent in this case, because the patient is a passive part of the environment. Uh, Tutor is a multiple agent thing, okay, because you have you have a student and a teacher, say that's the tutoring environment, and there can be interaction between the tutor and the teacher. So it's really a multi-agent thing. Right. So this gives you examples of different task domains and or environments, and how you characterize them based on the attributes that we have defined, or we have characterized environments using those attributes. So it's useful to try and create such a description for your problem. Okay. Now we come to agent types. So now we have looked at environment types, and now we want to look at agent types. Okay. This will determine exactly what kind of algorithms or even representations you will use. So we are going from simple to complex. So you have simple reactive agents, or what are called reflex agents. So these can be modeled by simple table driven kind of situations, right? If it's like this, do this. If it's like this, do this. So for example, you may have temperature controllers, right? So there's a threshold temperature. If you exceed that temperature, start the AC. Okay. If it is below that, you know, now you may say this is just a controller, but yes, it is a controller, but it conforms to this agent model, right? Think of it as a simple agent where there's an environment. You are sensing it using a temperature sensor, and you are acting to either do nothing if it is below the threshold, and you are acting to switch on the AC, for example, or similar thing can happen with a heater if the temperature is, above the threshold, so on. So you can model a lot of control systems like this. So they are simple reactive or reflexive agents, right? Then you can have rule driven agents. For example, you could think of how you could in principle imagine tax. You file tax returns. So if I give all the data to a program, it should be able to pick all the necessary things, pick all, I mean, so all these tax experts or these chartered accountants who advise you on tax and all that, it they can be in principle replaced, because really it's a series of rules. Okay, if your income is so much, and then you pay so much tax, and there are certain rules which tell you can make certain deductions, and so on and so forth. Of course, those rules interact, and you can get different tax liability based on which rules you choose, because multiple rules may be applicable, and there may be groups of rules which are mutually exclusive. So if I could apply one rule, I get a certain tax liability. I apply another set of rules, I get another tax liability, and so on. But in principle, they are all rules, and it's only a question of searching a very large space of possible endpoints, starting from my income and some other properties. So you can have rule-driven agents, and these can be modeled by situation action rules. We will see later on so-called rule-based expert systems. So you could build, in principle, a rule-based expert system as a tax consultant, for example. Uh, by tax consultant, I mean something that basically calculates your tax and tries to tell you that if you do this, 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 and this, you will end up paying the minimum amount of tax. Then you can have model driven agents. So these construct models of the task environment. So now notice what this is doing. Okay, they have to model the entire environment, then do the actions, see how the environment changes due to this, and essentially simulate. So you have to simulate things and then decide what you will do. Okay? So you need to build a model of the environment within the agent itself. So a lot of automatic control of large complex systems will have this feature. So there may be multiple active entities in a plant, and it's necessary for you to model all of them to decide what will be the best action to take. Yeah, so we'll talk about deductive, inductive a little later. Question is, are rule-driven agents based on deductive reasoning approach? Yes, they are, because the rules are already fixed. All you have to do is navigate the entire space of outcomes that different rule applications will give you. So they are in the larger sense deductive. That's right. Then you have goal-driven agents. Goal-driven agents, apart from having models, can also have goals. Okay, so you may want to say something like, maximize the plant output. So the action is not simply, do this or do that. There may be bunch of actions possible, but you have a goal. Okay, so very often there will be a goal of maximizing something or minimizing something. So those are called goal-driven agents. A general sort of generalization of this is something called utility-based agents, right? So in this case, there may be multiple goals, and you have to basically optimize utility, where utility is some kind of a function of multiple goals. So you may want to go maximize, say, profit. At the same time, you want to minimize tax. At the same time, you may want to, do something else, which uh, be socially relevant, or whatever kind of goals you have set for yourself. So there may be multiple goals, and some of those goals may be not necessarily aligned. That is, if you try to improve on one goal, then the other goal sort of decreases or goes down. Performance on that goes down. So when you have such a situation, that is, you have conflicting goals, and obviously you have multiple goals in that case, then you have to do trade-offs, right? So goal-driven agents essentially have a single goal: maximize this, minimize this, or something like that. So then you have utility-based agents. So when you have multiple conflicting goals, then you need what are called utility-based agents. And very often you may have to model them using game theory. Finally, you have learning agents. So F is basically finding the best action. Okay. So you can have a learning agents where this finding the action can keep changing based on changing dependencies. Okay. So basically you may have to learn from data. So what action you do may actually depend on what you are just on what you are seeing, but on the on your ability to kind of learn from what has happened in the past, right? So that's the most general kind of agent. And this often happens because the world changes. So if your environment is something where the task environment is not totally in your control, things keep changing. For example, take climate change. Okay, so if you, for example, if you are trying to build an artificial agent which is doing something, for example, maybe controlling a plant. Okay. But you see that if I do certain things, my consume energy, my carbon dioxide is going up, because of which certain climate change can happen, and so on. And climate change was not part of your vocabulary or repertoire or whatever it is, maybe 20 years ago. People were not bothered about climate change. Now climate change has become a major issue, right? So what is happening? For example, what do humans do? Humans now learn about all these things and then factor them in the environment. So for example, how do I now change my algorithms, control algorithms for the factory, let us say, so that now climate change is taken into account. Uh, so that's an extreme example, but you can think of many more examples where this happens. So rules change, for example. So for example, if you are driving, if it's a self-driving car, you go from, let us say, a country where you drive on the left side of the road to a country where you drive on the right side of the road, right? So the moment you are doing that, clearly there is a change. Now you have to kind of learn afresh various things that you need to do. So the most general kind of agent has to be a learning agent. So it will be the most complex agent. Okay. Now, what is the focus of our course? We have seen that basically we have to design agents. So our course goals are basically design agents in different task environments. And if you want to kind of formally define it, we will say that this function f, which you saw a little while ago in the previous slide, you have to basically design this f, where s is the set of states, right, of the environment. P is the set of percepts, so it's whatever you are able to sense. You may not be able to sense everything. K is the knowledge base or history or whatever. This is basically everything that you know. You know about the physics or laws of the world, or you know about historically what has happened. That is because it may not be a simple environment. It may be an environment where past affects the future. And knowing all this, you come up with a suitable, appropriate action, right? And our job is to basically represent all these things and then try to define or design a function f, which is the find action function, right? It takes all these things as arguments and produces appropriate behavior. In this case, outputs a suitable action, right? So to successfully build such agents, we need appropriate representations for S, that is the state of the environment, percepts, what is being sensed and how I represent what is sensed, all the knowledge that the agent has, and finally the nature of the action. This may be simpler than others, and then have a suitable algorithm that implements F. That is, it learns or figures out what should be the action, provided I have all of this. From all of this, I need to be able to design an algorithm which implements F. So that is going to be what our course will do. And there are two main approaches. So somebody mentioned deduction earlier. So we have a top-down deductive approach where you already have knowledge of the task and the domain to be, the task domain and what is to be implemented, and we have to just implement the agent. So the task, the tax agent, for example, was one such, right? Many others will be inductive or bottom up. That is, we do not have knowledge about the domain, and an agent has to learn how to act. So you look at the existing data and then learn from that data and come up with a model, then use the model to act in the world, right? And of course, you can have an intermediate situation or a hybrid situation where you have partial knowledge about the task, but you also need to learn. So you may have to do both. From the partial knowledge, deduce something, and then use data to learn something, combine the two, and come out with a suitable action, right? Very often this is the mode you are in. So you start perhaps with nothing. Supposing you are learning, for example, a child learns language. You start with nothing, but then slowly you gain a few words. You become you learn a vocabulary. Then you learn small sentences and you express yourself through small two-word sentences, or maybe just one-word sentences where you point at something and so on. And gradually you acquire the full language, right? And then you are able to express complex thoughts. So this is the general situation. The general situation is that you are never in a totally bottom-up or a totally top-down case. Well, not never, but mostly you don't have such task domains. Most task domains are hybrid, right? You learn something and you would like to use that learning. At the same time, you are learning more.